Welcome. In this video, we'll explore acid-base titration, a foundational method in analytical chemistry. Titration helps us determine the concentration of an unknown acid or base through a carefully measured neutralization reaction. Let's break down the key concepts and methods step by step. What is titration? Titration is a type of volumetric analysis where we use the volume of a solution to determine the concentration of an unknown solution. The goal is to reach the equivalence point, the moment when both substances have reacted completely. It includes acid-base, redox, precipitation, and complexometric titrations. Let's clarify the core terms. The titrant is the solution in the burette, and the analyte is in the conical flask. The equivalence point is when the number of moles of acid equals that of the base. The endpoint is the visible signal that the titration is complete, usually a color change due to an indicator. Acids and bases come in different strengths. Strong acids like hydrochloric acid and strong bases like sodium hydroxide fully dissociate in water. In contrast, weak acids such as acetic acid only partially dissociate. This affects how titrations behave and how pH changes during the process. Indicators play a vital role. Substances like phenolphthalein and methyl orange change color depending on the pH of the solution. The right indicator must be chosen based on the strength of the acid and base used in the titration, ensuring the color change aligns with the equivalence point. There are three main theories that define acid and base behavior. The Arrhenius theory describes acids as substances that produce hydrogen ions, and bases as those producing hydroxide ions. Bronsted-Lowry theory defines acids as proton donors, and bases as proton acceptors. The Lewis theory is broader. Acids accept electron pairs, while bases donate them. Some acids can donate one proton per molecule. These are called monoprotic acids, like HCl. Others, known as polyprotic acids, can donate more than one, like hydrogen sulfate. Titration curves of polyprotic acids have multiple equivalence points due to their stepwise dissociation. This titration curve compares strong acid and weak acid reactions with a strong base. A strong acid starts with a lower pH and shows a sharp change near the equivalence point. A weak acid starts at a higher pH and has a more gradual slope. For weak acid versus strong base: 1. Initially, only the acid is present. 2. As titration proceeds, a buffer forms from acid and its conjugate base. 3. At equivalence point, the base has fully neutralized the acid. 4. After equivalence, excess base dominates the solution. Let's do some pH calculations. The titration formula is based on the reaction stoichiometry. For simple acid-base reactions, use MV equals MV, where M is molarity and V is volume. This allows us to calculate the unknown concentration using the known values from the experiment. First, for a 2.0 times 10 cubed MHCl solution, since HCl is a strong acid, H equals 2.0 times 10 cubed. pH equals log 2.0 times 10 cubed equals 2.70. Next, for 0.1 mNaOH, NaOH is a strong base, O equals 0.1. Po equals log 0.1 equals 1. So, pH equals 14 minus 1 equals 13. Now, let's calculate pH for weak acid and weak base. First, 0.1 mCHCOOH, a weak acid. Using Ca equals 1.85 times 10 to the power of 5, we calculate H as 1.36 times 10 cubed. pH equals log 1.36 times 10 cubed equals 2.87. Second, 0.05 mCH nitrogen dihydride, a weak base. Using Kb equals 5 times 10 to the power of 4, we get O equals 2.5 times 10 to the power of 5. Po equals log 2.5 times 10 to the power of 5 equals 4.6. So, pH equals 14 minus 4.6 equals 9.4. To perform a titration, first fill the burette with the titrant of known concentration. The analyte goes into the conical flask, along with a few drops of indicator. Slowly add titrant while swirling the flask. Stop when the indicator changes color. This marks the end point. Note the burette readings to calculate volume used. To conclude, acid-base titration is essential in determining unknown concentrations in a solution. Choosing the correct indicator ensures accurate detection of the endpoint. It's important to understand the roles of titrant, tetrand, and the equivalence point. Titration curves also visually show how pH changes throughout the reaction, helping us interpret results more effectively. Acid-base titration is more than just adding one liquid to another. It's a controlled process requiring accuracy, knowledge of chemical behavior, and interpretation of data. Mastering it builds your foundation in analytical chemistry and prepares you for more advanced lab work. Volumetric analysis, especially acid-base titration, is essential in many scientific and industrial applications. It helps determine concentrations and provides insight into chemical reactions. Here a video example of perfect titration.
Thank you for watching and learning with us. We hope this presentation has deepened your understanding of acid-base titration.